Okay, good morning everybody. In this class we shall discuss about the RE transistor model. In the earlier classes we have seen that an amplifier has an input impedance and it definitely loads a source from which a signal is applied to it, and it amplifies the input voltage or input current, therefore it has some gain. And the output side, when you connect loads, for different loads the gain changes. For large load resistance the gain falls, while for low load resistance the gain falls, and for large load resistances the gain increases. That means a transistor exhibits some output impedance. Now given the model of a transistor in terms of the input impedance, output impedance, and the voltage gain, etc., we have seen how to compute the voltage gain of the amplifier, effective voltage gain of the amplifier, given the open circuit voltage and then short circuit currents of an input source. Now the question is, given a particular circuit, transistor circuit, what kind of input impedance does it exhibit, and how much of output impedance does it exhibit, and what is its gain? So once we complete this, the transistor analysis is complete. So let us now discuss about an RE transistor model, the RE transistor model, which can be applied to find out these parameters given a transistor circuit. And using this information you can derive, or you can design a transistor circuit once the input impedance, output impedance, gain, etc. are given. This is the design problem. Now there are different transistor models available which are applicable for different applications. Now in a transistor amplifier, we have seen that the transistor amplifiers can be classified as small signal amplifiers and large signal amplifiers depending on the amplitude of the input signal. So that is to be amplified. Now out of the small signal amplifiers, or for small signal amplification application, that you can use certain transistor models. So these models are there are several models that can be used. The popularly used models for small signal amplifiers are the RE transistor model, the hybrid parameter model, which is known as the H parameter model in short, and other models are also there, Y parameter model, Z parameter model, etc. are there. But these models are very popularly applied for the transistor analysis. These are models used for low frequency analysis. Models for low frequency and small signal analysis. Now for high frequency analysis, say you are interested in the RF amplifier in a communication receiver. It is a high frequency application. You have the input frequency running into several megahertz. Depending on the application, it ranges from megahertz to millimetric waves. So in such circuit analysis, we use the high frequency models, again small signal models. So these models, the high frequency models, are the hybrid pi model, and the Y parameter model. So this is the classification of the models that are applicable for small signal analysis. So these are for low frequency applications and these are for high frequency applications. Out of these, now we shall discuss about the RE transistor model. Now we know that in a transistor, say a PNP or an NPN transistor, say in this application a PNP transistor, on the input side between the emitter and the base, we have one diode that is present. So that means equivalently you have a diode here. Now with in common base configuration, this is what we use. Base is common to both input as well as output, and the input signal is applied to the emitter here. So on the input side, what the signal sees or the source sees is a diode which is forward biased, and this diode, depending on the voltage, it gives rise to certain emitter current. Now on the output side, there would be some collector current flowing, and the collector current is almost equal to the emitter current. The base current is 1 by beta plus 1 times the emitter current, whereas the collector current is beta times the base current. Therefore, collector current is beta by 1 plus beta times the emitter current, which is approximately equal to the emitter current itself. Hence, on the output side, there is a current controlled current source. It is a current source which gives rise to the collector current, and that collector current is proportional to the emitter current, and it is almost equivalent to the emitter current. How do you draw this conclusion? From the output characteristics of the common base configuration, so we know that, so the characteristics is something like this. This is VCE and this is IC. VCB versus IC, this is the characteristics. So the collector current is proportional to the base current, or beta times the base current. And the current is almost independent of VCB. Whether VCB is small or large or has intermediate values, the collector current is only dependent on IB. And you can also express it in terms of IE. So the corresponding emitter current may be IE1, IE2, IE3, and so on. Therefore, on the output side, the transistor can be modeled as a current controlled current source. It is a current source whose value is controlled by the input current. And as far as the input is concerned, it is like a diode. Now, so this is the model of a transistor. Now from this model, we can easily derive the information regarding how much of impedance does it offer, and how much of gain does it offer, and so on. Now let us draw these conclusions, or let us derive expressions for these from this model. Please note that as far as amplification is concerned, so we are interested in the alternating signals, the effect on the alternating signals. So when there is an emitter current, that means the alternating emitter current, there is a alternating collector current component, and the impedance, input impedance, is for an alternating emitter current, not for the DC components. As we have seen earlier, the emitter current here has a DC component, that is the quiescent point value, the biased quantity, plus the alternating component. The small letter here indicates the alternating component, and the capital letter indicates the biased component. Similarly, the collector current here is the biased current plus the alternating current. And when we talk about the small signal analysis, we are not interested in the biasing. We are interested in the amplification, input impedance, etc. for small signals. Hence, we use only these quantities, the alternating quantities, and let us find out the model for the alternating quantities. So the model here is like a diode for on the input side, and on the output side it is the current controlled current device. Now for a diode, what is the input impedance it offers? So if you look at the characteristics is like this. The characteristics is like this, and we bias it somewhere here, and we apply alternating voltage signal around this value here. And so this is responsible for some alternating base current around the biasing value. So this is the peak to peak amplitude of the alternating base current, that is AC, and this is the peak to peak value of the alternating base to emitter voltage that is applied. Now what is the input impedance it offers for an alternating voltage that is applied here? By looking at the characteristics, is it the static resistance or the dynamic resistance? So it is the dynamic resistance, which is given by the slope of the curve around the operating point, quiescent point, and that gives us the input impedance, and this is equal to 1 by RE in the case of the transistor. Okay, for this voltage, peak to peak voltage, this is a peak to peak current that is obtained. Now this delta VBE by this delta IB is the alternating component of voltage divided by the alternating component of the current, which can be given by the inverse slope, and that is the impedance that is offered to the alternating signal over here. Hence, the input impedance of this transistor here, which can be expressed as RE, is the inverse slope of the input characteristics around the biasing point, around the Q point. And this is known to be, we know that this is equal to 26 millivolts by the emitter current, IE, for a diode. For a diode, the impedance, this impedance is the slope of the diode equation, and we have derived earlier, an expression for it, and we got that as Vt by the diode current, or 26 millivolts by the emitter current in this particular case. and if IE is 1 milliampere, RE is 26 ohms as an example. So that is the order of the input impedance this transistor offers under common base configuration. So how much is the input impedance it offers? It may be a few ohms to few tens of ohms, which can be obtained from the slope of this diode. Hence, as far as small signals are concerned, now the model can be expressed in this form. As far as the input is concerned, it is a resistance whose value is equal to Re, and an expression for Re is given, and the output side is a current controlled current source. So this is the model. Now let us look at the output side. Is there any output impedance? So that is exhibited by the transistor. Now please note that from this characteristics, with change in output voltage, we exhibit, if this is the Q point, if the output voltage changes, that means the VCB changes from one value to another value. If there is a current change, corresponding current change, then we say that there is some output impedance. Output impedance is not infinite. There is some finite value, because this is what we are interested in. If you connect a load here, so due to the loading by the load, does the voltage drop? Or no, does the current change? So due to different load resistances, is the current constant or does it change? Now the current remains constant if it is independent of the voltage. Now this curve has some slope. It is not 0, but there is some amount of slope, but the slope is almost 0. So for all practical purposes, you can change the slope. You can consider the slope as 0. If the slope is 0, so the current, there is no change in the current with voltage change. And when do you get voltage change? When you connect different load resistances, you will find certain voltage, because the voltage is equal to the load resistance into IC. Now by connecting different load resistance, does IC change? Now change in IC is negligible. Therefore, the output impedance is infinity for all practical purposes. It is of the order of mega ohms or hundreds of kilo ohms to mega ohms. The output impedance is, which can be treated as infinity. Output impedance is infinity. So for Z0 is equal to infinity in a common base configuration. Hence, the model can be expressed in this form. So this is the model for the transistor in common base configuration. And this current is equal to alpha times IE, and this is IE, and this alpha is beta by 1 plus beta, which is approximately 1. Hence this is the model, the RE transistor model for common base configuration. Once this model is available, we can use this model in a transistor circuit, in an amplifier circuit, and we can determine how much is the overall voltage that can be obtained, and so on. In a transistor amplifier circuit, please note that it includes some other resistances which are used for biasing purposes. For example, here R1 and R2 come into picture, and RC comes into picture here. So including all these resistances, it becomes a transistor amplifier circuit. Now, when you introduced all these resistances in the circuit, how much is the gain it offers, and the input impedance it offers and output impedance it offers are to be determined. So to determine that, you can use this model for the transistor. Transistor can be replaced by this model. And simple Kashyap's voltage laws and current laws can be used to analyze the problem and determine the quantities of interest. Now let us look at, or let us derive a model for common emitter configuration, because common emitter configuration is the configuration which is very popularly used because of its characteristics, certain interesting characteristics like the voltage gain and current gain and a large power gain. So before going to that, let us summarize the characteristics of a common base amplifier. Input impedance is of the order of a few ohms, a few tens of ohms. So current gain is approximately 1. It is equal to alpha, which is of the order of 0.99, therefore it is approximately 1. Output impedance is very high. It is of the order of mega ohms, a few hundreds of kilo ohms to mega ohms. Now, how much of voltage gain does it offer? Voltage gain depends on the amount of load resistance you connect here. Please determine the voltage gain here. So voltage gain is output voltage divided by the input voltage, alternating signals, when some load resistance is connected. And we know that the output voltage is RL into IC or alpha IE, that is output voltage, and the input voltage is RE into IE, or when you apply VI, the IE you get here is VI by RE. So this is the expression. Therefore, it is equal to alpha into RL by RE. As an example, when you used a 10 kilo ohm resistance over here and the input impedance is say 25 ohms, how much gain do you get? Gain is 400. That is the amount of gain you get. Now let us derive a model for a common emitter configuration. In the common emitter configuration, we apply a signal to the base. The emitter is common to both output and input, and we connect the load to the collector. So here we apply the input. Now, what is the input impedance that is offered by the circuit? Here also you have the diode, input between base and emitter, but the current that flows through the base is different from, is a fraction of the diode current. Actually, IE is 1 plus beta times IB. Now the current that flows, therefore, IB through the transistor is IE by 1 plus beta. We have seen that when a voltage of Vi is applied, how much of IE flows here? The IE that flows here is equal to Vi by Re, where Re is the forward dynamic resistance of a diode. We have seen in the CB configuration. So here also please note that it is a diode. So when Re flows, how much of IE flows here? So Vi by Re, amount of IE flows through the transistor. That means from the input source, how much current is drawn? The current that is drawn from the input source is IE by 1 plus beta, and the same thing can be expressed in terms of Vi. So that is Vi by Re into 1 plus beta. So let me use the small r as the symbol. Hence, the input voltage to current ratio is equal to Re into 1 plus beta. That means the input impedance is 1 plus beta times the diode forward resistance Re, which is of the order of a few ohms to a few tens of ohms. Now the input impedance is larger than that of the CB configuration by 1 plus beta, by the factor 1 plus beta. Why is it so? Now the input current that is drawn from the source is much less than, is 1 by beta times, 1 plus beta times less than the input current which was being drawn in the CB configuration, because input was connected to emitter directly, whereas now it is the base that is connected directly. Now when beta is 100 and Re is that 26 ohms, when IE is 1 milliamp here, so you will get 100 into 26, 2.6 kilo ohms as the input impedance. Now for larger emitter current, Re is going to be smaller than the 26 ohms in the example which we considered earlier, and Ri is typically about 1 kilo ohm, is of the order of 1 kilo ohm. The same result can be obtained by expressing an intermediate model for this transistor. Now between the base and the emitter, we have the diode, and here we have the current source, current controlled current source. This is collector, this is base, and this is emitter. So this is the model which we got, or which we have used in the common base configuration. Please note that in the common base configuration we use the same model. Between the emitter and the base we have the diode here, a PNP transistor, therefore the diode polarity is on the side. Had it been an NPN diode, it would have been, the polarity would have been opposite here. And between collector and base you have the controlled current source. Now the same thing is used here also. The only difference being in how you are applying the input and between which terminal and which terminal you are taking the output. So please note that in this particular case this is the input. Between base and emitter the input is being applied, and the output is being taken between the collector and emitter, not between collector and base. Hence, by substituting the same model here, so you get this model. The same model which we have used for common base configuration is being used here. So this is the model. Now equivalently we have RE here, and we have this alpha times IE as a collector current here, where so this current is the total current, this current is IE. Now when this is IB and this is alpha IE, IE is equal to IB plus alpha IE. Therefore, the input current IB is 1 minus alpha times IE, and the same thing is equivalent to beta plus 1 into IE. By substituting the conversion or the relationship between beta and alpha, we can show that this is the same thing, this is equal to this. Now the voltage, when an input voltage of Vi is applied, the Vi is equal to IE times Re. So Vi by IB is Re into 1 plus beta. Therefore, and Vi is, I repeat, Re into IE by IB. Therefore, this is equal to 1 plus beta. Oh, there is a mistake here. This is IE by 1 plus beta. So therefore, the 1 plus beta into Re is the input impedance. Hence, the same expression can be obtained by using the common base model itself in the common emitter configuration by changing the input side and output side. Now, how much is the output impedance when in the case of a common emitter configuration? Now, before going into the output impedance, Please note that in the common emitter configuration, the input to output current ratio is IC is equal to alpha IE, and in terms of IB, so this is going to be beta by beta times IE, or this is going to be alpha into 1 plus beta into IB. So that is equal to beta into IB. IC is equal to beta IB here, and in terms of IE, it is alpha into 1 plus beta into IB. So beta IB is the collector current which flows. So you can express the collector current in terms of the base current, and that is this. This is the expression. This is okay. Now let us compute the output impedance. Similar to the common base configuration, so let us look at the output characteristics. The output characteristics of a transistor in common emitter configuration is the relationship between VCE and IC. So the relationship is like this. And in the active region, say you are operating at this point with this much of VCE and this much of collector current. Now by changing the output voltage, so we expect some change in the input current. If this is the delta VCE that is applied, so we observe a small amount of delta IC in the biasing quantities. That means when from the output circuit, when you connect some load, so depending on the load, the current varies. Current varies depending on the load. If the load resistance is large, that means the voltage is large, and the current is, you will find that the current is large or current is small. And when the output voltage is small, that means the current is, the load resistance is small, you will find the current increasing, and under short circuit conditions the current is very large. So this is what happens. This is what I am talking of in terms of alternating components. So the output impedance in this particular case becomes a delta VC by delta IC, and that is the slope of this curve, inverse slope of this curve around the quiescent point. This is 1 by R naught. And once you are given as the characteristics and the Q point, by finding the slope of this curve, you can determine how much of R naught the transistor exhibits. And please note that it depends on the operating point to some extent. The slope here may be slightly different from the slope here, and it may be slightly different from this one. And if the operating point is close to the saturation region here, the slope is somewhat larger than this. So the operating point also decides about how much of output impedance and the gain, etc., the transistor offers. So given the characteristics, one can determine the slope. And in the case of a common emitter amplifier, the slope is of the order of 40 kilo ohms. Now with these quantities computed, we can determine the model for a common emitter configuration. So the model can be expressed in this form. So here the input impedance is going to be beta times Re approximately, or 1 plus beta times Re, and this is beta times Ib, and there is an R naught, which is the inverse slope of the curves and which is of the order of 40 kilo ohms. So this is the model of a transistor in the common emitter configuration. So the same thing can be obtained, or the analysis, for the analysis of an amplifier circuit, we can substitute this model for a transistor and carry out the analysis. Alternatively, so this model can be used, the common base model itself can be used in this form, and we can carry out the analysis, because it is the same. What we have done now is we have used the common base model itself. This Re and alpha IE are for the common base model actually, and the same thing is used, and the only difference being the connection, the input and output connection. Now using this model itself, we have obtained a different model for common emitter configuration. Now the common emitter configuration, in the common emitter configuration, we expressed it in terms of its input impedance and its current gain and the output impedance. So this model is a direct model for common emitter configuration. And I repeat, we have obtained this model from the common base model itself. Hence, you can use any model. You can use the common base model or the common emitter model in an amplifier circuit, and you can compute the gain it offers, the whole amplifier offers, the input impedance the whole amplifier offers, and the output impedance the amplifier offers. So far we have been talking in terms of the input impedance, output impedance, and the gain of the transistor alone for alternating signals. Is when you substitute this in a circuit, it gives you the amplifier's gain and so on. Now I have to mention one more thing here. So that is the current gain. Now the current can be expressed, the collector current is expressed in terms of the base current here as beta times Ib. In terms of the emitter current, we have expressed it in the previous model as alpha times Ib. So please note that these two are related. Here also it is alpha times IE, but for convenience we have expressed it as a function of Ib as beta times Ib, but the expressions are interrelated, because here the input current is Ib, not IE. Hence we have used beta times Ib as the expression here instead of alpha times IE, which is still valid, still applicable. Now, how much is the current gain? So that can be achieved in this particular case. If you short circuit this terminal, then you will find that the output current is beta times Ib and the input current is Ib. Therefore, the current gain one can get is so minus beta. Now, if the current is expressed as a positive current, if the current is going inside, then the current gain is plus beta. Indeed, we consider the current going into the terminal as a positive current. Therefore, the current gain expression is plus beta. If you express it in terms of the load current, IL, as the current going into the load resistance, then it is minus beta. Now, when a non-zero load resistance is connected, so this current is going to drop further. The current gain is going to be beta times R naught by R naught plus RL. So because of the division, further division between R naught and RL for the output current, we have to introduce that term to get the current gain. This is a product, this is a byproduct of this model. We have used this model in the circuit where RL is used. So this is how we can determine the current gain, etc., when you use this model in a circuit. So the circuit, to represent the circuit, I have introduced one transistor here, but if you have another resistance here, you have to introduce that resistance here and then compute the overall current gain, etc. So that is how you apply the model to determine the gains, input impedances, output impedances, etc. of transistor amplifiers. Any questions?